Hello, this is James Keene at Binary Mechanics Lab, bringing more light and happiness to your pursuit of physics truth. Today we're going to look at the non-zero proton electric dipole moment derivation from first principles. Now, as you probably know, in the physics literature, there are a number of expressions where basic physics constants such as vacuum light speed, Planck's constant, elementary charge, fine structure constant alpha, and so forth are shown to be related to each other. But those aren't derivations from first principles. Let's say we have an equation with Planck's constant on the left equals something on the right, and on the right we have other measured physical constants. Well, those aren't first principles. Those are measurements. Okay? So it's important to keep in mind what a derivation from first principles of a theory means compared to equations you might have seen in the physics literature, which simply show some relationships among basic measured constants. Okay, let's get going here. The proton electric dipole moment, EDM, equals this value shown here, calculated from positions of charged one-state bits in the central baryon bit cycle, which I'm now calling the proton or hadron bit cycle, model of the proton. Elementary charge E and the estimated fundamental length constant, then called D, but now denoted by the capital letter L, based upon binary mechanics postulates and nucleon scattering data. This EDM is deemed to be accurate to at least 7 digits based upon the codata accuracy for elementary charge, integer position coordinates are exact, and 3, the assumption that the charges are centered on the coordinate grid shown, and 4th, only one state bit circulating in the central baryon bit cycle. The binary mechanic prediction of zero electron dipole moment has been confirmed by observations conducted by 2 independent labs deemed to be reliable. The present non-zero proton EDM result is consistent with all experimental measurements to date and is discussed regarding P and T symmetry issues. Figure 1 shows the electric charge positions in the central baryon bit cycle. The electric charge property is associated with the M-type bits in spot units. The central baryon bit cycle I now refer to as the proton or hadron bit cycle. You might want to look at the previous video, first ever derivations of basic constants from first principle, which provides background on quantized space, so you'll understand better what we're talking about right now. Now, the centers of the bit loci, which are approximately 0.6 femtometer cubes of quantized space, are viewed from the XY plane and rotated 90 degrees to see it in the YZ plane, showing charge densities, which again are the M-type bits in binary mechanical space. Schematically, the red indicates 2 plus charges, light red and orange is 1 plus charge, and for the negative charges, yellow means 2 negative charges occur at that location or coordinate in the spot cube space, and the light yellow and orange indicates 1. Now, does that look like 0 EDM for the proton to you? It doesn't look to me. So let's look more carefully. Table 1 summarizes data pertaining to the research question of proton EDM value. These are the charges of M-type bits shown in this column. Here is their position within the spot cube, and these are going to be charge vectors, as it were, or displacements actually of charge from the center of mass of the M bits represented. Okay, so the legend here is we got the unconditional bit operation and the strong bit operation is U and S respectively. The spot types and names from table 1 in a reference. Q is the charge sign. The exact XYZ coordinates are R1 through 3. The center of mass of these one-state bits is going to be this vector. This Q of the difference of the two vectors is going to be the intermediate EDM result for 21 positions. The center of mass for the 21-bit positions was 1.7 da 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 da, and this is a vector along actually the solid diagonal of the spot Q connecting the electron and positron spots. Okay, using these coordinates pegged to the centers a bit below psi cubes, the center of the spot cube is 1.5, 1.5, 1.5. Hence, the center of mass is closer to the electron spot due to bit positions in neighboring spot cubes, shown in Figure 1, affecting the non-spherical proton shape. The products of the charge signs, Q and position vectors, R minus C, were summed to an EDM vector of this. Also on the same positron to electron solid diagonal of the spot cube. Thus, the EDM axis of the proton appears to be the same as that of the zero EDM electron and the intrinsic electron spin. The EDM vector length multiplied by elementary charge E and binary mechanics length constant D, now designated by capital L, expressed in centimeters, gives a proton EDM estimate of 8.5 ECM, as shown here in equation 1. Given the extremely small uncertainty in this result, the calculated value is a huge number of standard deviations from zero, confirming the hypothesis of non-zero proton EDM with almost 100% confidence. Now, these guys, I won't even attempt to pronounce their names, have reported an upper limit for proton EDM of about 5.4 to the minus 24 ECM. The present result is some 8 orders of magnitude smaller, but in the words of Johnny Rivers, may be just a little plaything, but on the right side of town regarding the observed upper limit. Although work designed to measure proton EDM at a 1 to the minus 29 e to centimeters level may hit the newsstands down the road, it seems the present result will survive for quite some time, or as Johnny said, it is hard to find nice things on the poor side of town. The 2 to 42 possible hadron configurations need to be parsed into groups representing particle categories. Specifically, the proton group would include all the bit functions representing proton time phases, momentum vectors, energy levels, etc. Then the proton EDM could be recalculated with the various selections of proton bit functions representing properties of theoretical or experimental interest. Work along these lines is probably necessary to calculate proton EDM estimates relevant to particular theoretical concerns or engineering tasks, and to further weigh the veracity of the present proton EDM calculation. Meanwhile, the present non-zero proton EDM result may be, as Johnny says, the greatest thing this boy has ever found. Why? The reader can decide how bad the carnage might be in the fallen physical theories, including those assuming continuous space-time and those depending upon T and P invariance. It may take a miracle here. According to Olive et al., a non-zero value is forbidden by both T invariance and P invariance. In other words, if the present non-zero proton EDM report is correct, it's going to take a miracle to salvage T and P invariance, leaving P invariance as a homework assignment. Let us look briefly at T invariance. As discussed previously, the arrow of time is clearly unidirectional. Can anybody use the pattern of 1 and 0 bits on a computer hard drive and determine what the pattern was at one arbitrary unit time previously? All those who can do that, now is the time to step forward. Consider a single one-state m-bit related to fermions anywhere in a bit function for a system state at time tick t equals 0. With the four fundamental bit operations, this bit locus could be in the one state due to 1, an unconditional bit motion into its spot unit, or 2, a strong bit operation scattering event. Exactly how could it be known which occurred? For reverse data processing, or motion of objects backwards in time, this problem must be solved unambiguously. That was the easy case. Uh-oh. How about a single one-state bit of the L type related to bosons in a bit function? At tick equals 0, this bit could be in the one state due to 1, the unconditional bit motion, 2, a strong bit operation scattering, 3, the presence of an electric potential causing might to light loci motion in the scalar bit operation, or 4, a magnetic potential causing might to light motion in the vector bit operation. At this point, the analyst is probably going to be on the knees praying for help, because the selection among options 2 to 4 above depends upon the bit configuration at t equals -1, the previous time tick, which was different than what we have now at t equals 0. Now pick an arbitrary zero-state locus, which is related to neutrinos, and repeat the above steps to accomplish reverse data processing. Where was the one-state bit at t equals -1? In short, unless some genius can solve the above problems definitively, we might safely conclude that motion of objects backward in time is mathematically impossible. Let me look around and see if there's any geniuses in the room. My God, this place is crowded. It's packed. Unbelievable. One may travel backwards in the time, in effect, by reading about such work in quantum electrodynamics and chromodynamics to get a feel for what physics was like in a previous century. Of course, the reader is not actually going back in time physically, as depicted in science fiction movies. It may be more like a present-day anthropologist visiting a more primitive village to observe the superstitions of its peoples. Now, finally, our spokesman at the time this paper was written was Linda Jones. And her message to the physics community is in Give My Love a Try. How about that eternity part in her official statement? In the interest of fair labeling, she notes that binary mechanics is guaranteed 100% free of unhealthy singularities. So when you go shopping for new ideas in physics, be sure to read the fine print on the label and be sure that they're certified free of unhealthy singularities. We don't want any infinities to mess us up. Thanks for watching. I'll see you later. Bye-bye.